Actually, maybe we get. I mean, I might not do all of this because we've seen it before, so I won't even write it down. What is stress? What's the definition of stress? Force over. Yeah, etc. Strain.
Extension by unit original length.
Yeah. Okay. Elastic rope, length 12 meters, area 0.9560. The rope has Young's modulus 6.51 10 to the 8. So can you write this first number down? 12 meters is the length. Now, centimeters is 10 to the minus 2, isn't it? So let me just convert that next one into meters squared.
Minus 4?
Yeah, minus 4.
9.5 times 10 to the minus 5.
So can you write this down, please? Area equals 9.5 times 10 to the minus 5. You got that? And then Young's modulus is 6.51 times 10 to the 8.
6.51?
Yeah. 10 to the 8. And finally, the delta L, the extension is 1. And he would like you to calculate the force. Okay, so Young's modulus is stress over strain. What's stress? Force over area, and then delta L over L. Okay, so let's fill in the numbers. What did I say Young's modulus was?
6.51.
Yep, times.
10 power of 8.
Okay. Force we don't know. What was the area?
0.00.
No. What was it?
9.5 times 10 to the minus 5.
10 to the minus 5. The extension was 1, and the original length? 12. Okay, so we can get, if we all do this one now, get the F from that. I can't see, what was this number here?
9.5.
This one power though?
Minus 5.
Minus 5.
That's just right?
Yeah, minus 5. So, do we have an answer there for the F?
Yes.
What you got?
5.71 times 10 to the 11.
Oh dear. I got this one as the F. You got 10 to the 11 seems too big for a force. What did you get, Avenue, for this?
Nothing.
Oh my god.
I tried.
5 to the 8.
Oh yeah. It's 5153 times 0.75.
Okay, so that's
Yeah.
0.75, so then a 4 here, newtons. Okay, now next. Sketch a graph of force against extension for the rope and show that the elastic potential energy W stored in the rope when stretched. Okay. So first is force against extension. Well, we've seen this graph before, haven't we? So force against extension. So the graph will just be straight line.
Can you go up to
Yeah.
Didn't take long.
To here,
515. Is that 5?
5154.
Okay.
Sketch a graph of force against extension and show that the elastic potential stored in the rope when stretched at distance x is given by a half k x squared. Now, if I draw the rope, I'll draw it. For the moment, I'll just draw it on the ground, okay? So that's the rope. It's an elastic type of rope. So if I pull it this way with direct force F, then if it's balanced, there'll be a force to the left, and the force we get from Hooke's law will equal, what's Hooke's law? K KX,
Delta.
where, or delta X or delta L or whatever you want to use, okay? So X here equals delta L. Now, this next part, I don't know if anybody remembers this because it was a long, long time ago. Force equals minus Kx. I put the minus because it's going to the left. Does anybody remember a way to calculate potential energy from force? I'd be very impressed if anybody remembers this. Anybody?
Well, if it's
Was
MGH.
this half? No, it wasn't.
No, that's the answer, but I want to know how to get it, how to prove it.
How to prove?
All right, let me tell you.
MGH.
If you want to calculate the potential energy, and if you know the force, the way to calculate it is just do minus integrate the force. So here it would be minus integrate Kx dx. And what would that be? Oh, sorry, minus minus, so plus a half Kx squared. Let me give you another example of this. To the left for the moment, just for the moment. What's the force due to gravity here? F equals mg, but because it's going down, I'll put in minus mg. Potential energy will equal integrate minus f dx, which means integrate mg dx. Mg is a constant, so when you integrate, what is it? Mg x. And in this one, what does the x represent? It's like the height. So, point is, you can actually use this to get the potential energy from the force. A useful little trick. That's one way to do it, okay? By the way, think for a moment. What does that represent on the graph? What does integration represent on the graph? Area. Now, if I go back to my graph here, okay? Listen carefully. I said, Avenue, you can get your ice cream in a moment, just listen carefully. I said the potential energy equals integration of the force. Another way to say that is potential energy equals the area on the force graph here. So if this here is F equal to K delta L, or if you want Kx, if I call it delta Lx, if this here is X, then what would be the height here? It'd be Kx, wouldn't it? Because it's a lot just like y equals Kx, if the F is like the y. So if the x is x, then the height would just be Kx. What's the area of a triangle?
That's
Kx squared.
Yeah, a half
Kx
the
squared.
base by the height. So that's a half Kx squared. So you have two choices in the exam. You can say potential energy is the area on the force graph, or as a maths problem, you could also say which is the integration on the force graph. Is that okay? Can I go back to the question, or do you need to? Okay. A climber of mass 75 kilograms using the rope falls from A at the top of vertical cliff. One end of the rope is attached to the climber, the other end is attached to A. He falls freely for 12 meters to point B. And then the rope is straight but not stretched. Then he falls a further 2 meters. Okay. So let me draw that. He's up here at the start. And here he is here, and he's got his rope. Then he falls, but here the rope is 12 meters long, but that's its natural length. is not stretched, okay? So 12 meters is the length and 0 here is the extension. But then he falls another 2 meters. So now 12 meters is still the natural length, but now he's traveled an extra 2 meters. So that's the extension here. So far, is that okay? Alright. So what do we ask for first? What is the force on the climber at point C? Okay. So here, A, B, C. So I'm going to break this journey up into 2 parts. So the first one here, he starts at rest. Yes? I would like to know what the V is. So U equals 0. V I don't know. A is 9.81. T I don't know. S is 12. What formula can I use to get me the V?
We start off with
V
the
squared is
UT
equal.
plus half AT squared.
Hold on, I'm an ice cream problem here.
Or the U plus 2AS.
Keep talking.
Okay, we start with that one.
Do you need teaspoons?
I do actually. Thank you.
We use that one to determine V. And then when we get V.
Hold on, Brendan. I got some business to take care of here. Okay. Now back to the physics. I'd say this one. Remember this one? V squared equals U squared plus 2AS. Got that? So type that in, let's see what we get. So his speed here is 15.3 meters. Okay. And then his speed here at the end, what is it? It'll be 0 meters per second. Sorry, meters per second. Meters per second. And then up here at the top, I'll make space here, 0 meters per second. Starts, falls, and then what happens when the rope gets tight? He starts to slow down. The rope starts to pull him back. So when you look at the very, very, very bottom, he's not moving. There are 2 forces acting on him. What are the 2 forces? Gravity 1. So we're told, I think his mass is 75 kilograms. And then there's an upward force here. How could I find the upward force?
It's equal to the gravity.
Yep, that's true. But what's the formula for force in a string? Hooke's law.
Huh?
Hooke's law.
I didn't hear your question.
What's the formula for force in a string? A spring. Hooke's law. Yes. So I get F equals 75G. Yes? Then you get K delta X equals 75G. Now do we know the delta X? We do. It's 2. So I can use this to get the K. So I got K is 367.9. That's the K. So I have the K now. Now let's see what I was looking for. I'm looking for the resultant upward force at the climber at point C. No. Scrap that. When he hits the bottom, it's not balanced. So I'll have to undo that bit. Sorry about that. Can you look? This is what happens. He jumps out, falls, hits B, and then he starts to slow down at C. But he doesn't stop at C. What happens at C is then he starts to stretch back up. So the force, there's 2 forces going up. Well, I mean, there's one force going up and there's the weight going down. But the force going up is bigger. F is bigger than 75G. So they would like to know in the question, how much bigger is it? What's the difference? So what type of force is causing them to go up? Well, it's still K delta X minus 75G. That's how much force is going up. Does that make sense? If you look, I shall borrow these, Brendan. Don't worry, I won't break them too much. So when he falls down, the rope is pulling him up. That's the K delta X. And then his weight is pulling him down. But the question says they're not equal because he stops and then he'll go back up. Okay? So they would like to know how big that is. Now we know what the delta X is. What's the delta X? That's 2. The only problem is we don't know the K. But there is a way to find the K using energy. At the top of the cliff, what energy does he have? What type of energy does he have at the top?
Potential.
Just potential, isn't it? So potential energy would equal mgh. 75 times 14 times the height, times the g. So that is 10300. Now, example, when he's at B, what type of energy does he have? Kinetic and potential. When he's at the bottom, what type of energy does he have? No, he's not moving. Now listen, at the bottom, is he moving? No. So does he have kinetic? No. He's at the bottom, so he has no potential. But don't forget, he's attached to this rope, and this rope is stretched, and it has potential energy. And that's exactly what they asked you to do in the last question. The formula is there. A half K delta X squared. So we can say that's equal to a half K 2 squared, and therefore we have the K. So 10300 times 2 divided by 4. So I get K is 5150. So now I can go here and get the answer. (9,564 newtons). Do you need me to go back to? Does this part here make sense? This piece here.
Yeah.
It's okay? Yeah. All right. What's next then? All right. Well, the next part is actually kind of easy now. He wants to know what is the upward acceleration. So there's the upward force. How can we get acceleration from force?
Yeah,
F equals ma. What's his m?
75.
So 75a equals that. So therefore a equals 128 meters per second squared. Now, by the way,
that's very fast.
it is very fast, but you got to remember he's only accelerating while the force is, like why the string is really stretched out. What will happen is as soon as he moves up, the string will start to relax, and then that acceleration will quickly drop. So at the very, very bottom, for the first moment, it will be that acceleration, but only for a moment. Now look, you can see that from the marks. This one is 3 marks, whereas the second part was just 1 mark. Is that okay? Okay. C part. So you're building this shelf and you're given the density and we want the weight. So first we have to find the mass. So can you just please make note of these numbers? 30, 120 and 4 is the thickness. So 30, 120 and 4. Got those 3? Okay. Do you have those? So
It's hot.
it's 30, 20 and 4.
120.
So 30 is the first, is that what I said, 30?
120
120,
and 4.
and then 4 centimeters. Okay, so what's the volume there? It will be now he gives us the density. The density is 850. And he would like the mass and then the weight. So density equals mass over volume. So mass equals density multiply volume. So I got the mass is equal to 12.24 kilograms. And how do I find the weight? What's the weight? mg. So 120 newtons is the weight. So that's the first part done. Now, you put this mass of 5.1 kilograms on the edge of the table, and the table leg is 15 in. So in total, this will be 65 centimeters in from the edge, okay? We would like the two reaction forces here. So what type of problem is that? It's one of these turning force ones. It's okay?
Yeah.
How far in did I say it was? 65 centimeters. Wasn't it? And what was the mass? It was 5.1. So the weight is 5.1 times 9.81. So that would be 50 newtons. Now what did I say the weight of the table was? What was the weight of the table? Come on, don't just sit there looking stupid. What was the weight of the table? Did you not write it down? I think I said it was
the only one that I didn't write down.
120 newtons, was it?
They didn't even
The last term, sir, yes.
Yes, thank you. All right. Now, how long is this table? It is 120. So, yeah. Oh wait, that's not. Yeah, something seems wrong here. No, 65 centimeters.
15, and 40.
Okay. Yeah. The table is 120 centimeters, which I know it looks wrong here because I'm saying that this here is 0.6.
So it's 120 centimeters wide and it weighs 120.
What? Oh, that's a weird coincidence.
It is 55 centimeters wide.
55? Where's 55?
You know, it's 15 centimeters and 40 centimeters.
Yeah, 55. Oh, yeah.
55.
Thank you, Sayur. 55. And the weight was 120. Yeah, coincidentally, the weight and both the length is 120. Yeah. Right, so we would like, there's two reaction forces here. The first one is a distance of 0.15, and then this one here is 0.15 from the end of the table. So 1.2 minus 0.15. So that's a distance of 1.05 from the beginning of the table. All my distances are from the start of the table. All right. Are you writing this down?
This?
Yeah, this.
I'm taking notes.
No, that. Yes, this here. Are you writing this down? Yes. Yeah, revision. Are you writing this down?
I'm actually, yeah. I'm not writing all of it.
You know I have teacher translator, so when I hear students say, I'm not writing all of it, that means, I'm not really writing anything.
Everything. I have a separate.
You're just making it worse for yourself the more you talk.
Yeah. Like.
My notes? Gone. Right. We need to make two equations here. So the first one is the up force equals the down force. Got that? And then what's the other equation going to be? What's the other equation? How do we make the other one? Come on, the sooner we finish this, the sooner we're going home.
This is the last question?
We'll do this one and then we'll go. No, I don't. There might be another part to it.
Oh, the whole rotate clockwise.
The turning force. So, firstly, let's do the clockwise. Is the or clockwise or anti-clockwise? No, anti-clockwise. If I take it from here. Anti. What about this one? Clockwise. So 50.55 times 50. What about this one? Clockwise. Now, that should equal 0.15 or plus, what will be the last part here? 1.05 s, because they're the other direction. They're the anti-clockwise ones. Now, can you please write these down? I'll just put them into derive as two equations and solve it.
Wait, how is RMS both anti-clockwise? From where?
From the beginning of the rod.
Oh, okay.
Did you write them down? Because I'd like to just put it into derive to solve. Have you got it? Actually, I could do it in derive, yeah. Can you take on that? So the first one, Brendan, is
0.50
R plus S equals
170.
Yeah. And then the second one?
0.55
Yeah.
times 50.
Yes.
0.6 times 120
Yes.
is equal to 0.15 R.
Sorry, is that wrong, Sayun?
Wait, no. The second one's 0.6 something.
Yeah. Equals
0.15 R.
Yeah.
And plus 1.05 S.
Solve system, two equations, line 7, line 8, or an S solve. We'll do it as decimals. So we get 87.8 and 82.2. So the OR is 87.7 and then 82 point, what did I say, 2, wasn't it?
Yep. That's 120.
87.8 and 82.2. So that should be an 8 there. Elimination, matrix, whatever method you want. Okay. We've seen this before though, we've seen this a couple of times. Oh, good, that's the end of that. Now, just before we finish, there was one thing I was reading that I want to point out. It's one of these little weird things, not weird, but it's one of these things where if you're clever, you can figure it out. So, since I know you, I'll explain it to you. Can you look up here?
Thank you.
No, it's okay. It's okay. We're here to learn. Can we look up here at just this question, and then we'll finish with this part. Yes, can we look up, please? The pressure, can you see? The pressure of an ideal gas is given by this formula. Pressure is 1/3 rho, and then this thing here. This is the density, we know that, yeah? P is the pressure, but does anybody know what this symbol is?
R squared.
No, it's actually C squared. Now look, even if you don't know what it is, doesn't matter. Read the next question. The density is this, the pressure is this, calculate the RMS velocity.
So that's
So,
RMS.
that's the RMS, because they give you a formula, and then the next question they give you the temperature, the pressure, and the temperature, and what else? The density. Yeah, there is the density there. So that must be the RMS velocity. But if another way you're supposed to work it out is if you just look at the units, okay? What's the units for density? Kilogram per meter cubed. And what's the units for pressure? So let's do that. Let's just look at the units. So pressure equals, what was it? 1/3 density, this thing. So this thing equals pressure over density. Now, what was the units for pressure?
Newton.
Newton per
Yes.
meter squared. And then density?
Kilogram.
Kilogram per
Meters.
meter cubed. So if I multiply the top and bottom by meter cubed, they cancel. And then meter squared into meter cubed, meter. So you get here Newton
Per meter.
meters
On kilo.
per kilogram. Now we have to clean this up a little bit more. But Newton, what's Newton? F equals ma. So 1 Newton will equal kilogram meter per second squared. So let me put that in for Newton. Kilogram meter second squared meter kilogram. So what cancels?
Kilogram.
Kilograms. And what are you left with? Meter squared over second squared, which is meter over second squared. So the units of this c squared thing is meters per second squared. What's meters per second?
Velocity.
Velocity. So this looks like it's velocity squared. In fact, what it represents is the average velocity squared of the particles in the gas. So it actually represents the average velocity squared of the particles. So the reason I'm showing you this, Abanoop, please, we'd like to go home. The reason I'm showing you this is there's two ways to figure it out. You can figure it out from looking at the units. No, don't move. I know you're excited that we're nearly finished. You can figure it out by looking at the units, or you can figure it out by reading on in the question to get a context. Now, if we look at the marks, it will tell us what we need to do. So, if there was not many marks, what do you think they need? Do you think they just need a direct answer or a little proof like this? Direct answer. And then the more marks, the more we think we need this proof here. How many marks? One. So direct answer. You can say it is the RMS velocity. By the way, the RMS velocity means the velocity squared, the average velocity squared. But you can call it the RMS velocity. Okay, but I'll make note of that. This is also called the RMS velocity, which is the average velocity squared. They mean the same thing. Please write that down. You will forget it. And